Okay, we're going to have two different sections of notes in this video lesson. The first one is 2.2 graphs of functions, and we're just going to kind of review some basic graphing techniques. The details of the harder functions we'll kind of do as we go along, but for right now you should be pretty caught up on graphing lines and basic parabolas. So with piecewise functions, let's just look at the notation. We have one function. We do have two parts, and they each have their indicated domain. So we're going to graph the line y equals x for all the x's less than or equal to 0, and we're going to graph this other line for the x's greater than 0. Okay, so parent function y equals x, this should be no problem. Now we only want to graph it for x less than or equal to 0. So if you want, or if you need to, you can graph the whole line, but we're only going to keep this parent function y equals x for all of these x's. Now, when you learned this in pre-AP Algebra 2, you went ahead probably and graphed the whole thing and erased what you didn't need. And that's fine. For the more difficult piecewise functions, I'll even do that. For this one, just graph the piece you need. Okay? So for the next part, 1/2 x plus 2. Now, this is has a y-intercept of 2, so we'd start with 2. Now I'm going to go ahead and just already put an open circle there because I only want this graph, or this piece of the function, for the x is greater than 0, not equal to 0. And so my slope is up 1 over 2, up 1 over 2, and you can graph this quite easily. Alright, now we've actually already been practicing piecewise functions, so this shouldn't be too bad. What we haven't really been doing is writing domain and range down a lot for things like this. So the domain, all the x values. This graph would not be considered continuous because it's disconnected here, but all of the x values are included, so our domain is going to be negative infinity to infinity. Okay, now let's talk about the range. So the range, we start down here, forever down, so that's going to be a negative infinity. But because we have some discontinuity, we have a break in the range. We stop at this point, which is where y equals 0. Now, since that point is included, we put a bracket. And then we have all these y values that we don't include. We pick back up with y equals 2. We use a parenthesis because that point is not included right there. And then remember that negative infinity and infinity always have parentheses because they're not really technically numbers. Okay? Alright, let's look at the next one. Here we have g of x, and again, two pieces. The top piece is another line. So we start with 2, okay, and then we could go up 1, over 1. Here I'm going to go down 1, over 1, down 1, over 1, down 1, over 1. And we only want this piece for the x's that are less than or equal to -1. So that really starts right here. Okay, another way, if you don't like starting here, because now I'm going to have to erase that point, one thing we could have done, which I think if you are pretty good at graphing lines you're ready for, is to go ahead and find what g of -1 is. And g of -1, -1 plus 2, that would be 1. So I plot the point, -1, 1, and then I use the slope from there. This would be extremely useful if say these were like -6's. You wouldn't want to plot a whole lot of points unnecessarily. So let's go ahead and use that technique on the next one. Here we have g of -1. This time it also equals 1. Okay, these are the same two numbers, so even though this would be an open circle, there's already a point there, so I don't have to put an open circle. Alright, now with parabolas, this is just your basic parent function, so hopefully you're able to graph this. You could always just plug in a bunch of values and connect the dots, or you could think of it as transformations. This parabola, though, has a vertex at 0, and remember that there is an over 1, up 1, over 2, up 4, because it's a number squared, over 3, up 9. That is a way that you can graph this, but like I said, with the parent function, you really should just know this. Okay, so let's think about our domain. Our domain, again, is going to be all real numbers. Really, this domain is only going to get thoroughly thrown off if we have a stranger, function that's like parent function of a logarithm, or maybe a square root, or irrational, something that throws the domain off. Other than that, your domain is going to be all real numbers. Okay, range. This graph goes forever down, so its y values start at negative infinity. And there is no break in this graph or anything. We still need to make sure, though, that it's going all the way up, and it is. So range here is also all real numbers. Okay, let's move on to something a little new. You have talked about this, but I don't think you've actually used these words. The greatest integer function. I want you to write below this, the greatest integer not greater than x. Remember, we've talked about what integers are. They are whole numbers, but they can be negative. It can be 0. Greatest integer not greater than x. Okay, so let's do a table, and then we'll plot this. And once we get it plotted, I will refer back to something that you are familiar with. So let's think about 0. Let's just start with 0. What is the greatest integer not greater than 0? Okay, that's going to be 0. Now let's do something like 0.5. So we have a choice here. We can either we can think round down or round up, but we have to pick one that's not greater than this value. So if we pick 1, 1's actually greater than this. We don't want that. So it is essentially like a round down. Okay, even if you had 0.99 continuing, you would still have to go down to 0. Now once you hit exactly 1, that would pick 1 and so on. So let's get this first little part plotted, and then we can see if we can make a pattern. So we have 0, 0. All the way, all of these x values give me a y value of still 0, and then right up until this point. So I'm going to put an open circle there. Now as soon as you hit x equals 1, your y value, your output, is 1 as well. And you're going to have something else for 1.1, for 1.5, for 1.9. The y value is always going to be just round down to 1 until you get right up there, and that's just a boundary. Then we jump. Okay, this is something that is sometimes referred to as a step function. Okay, and now you have the equation that goes with it. A good example of this in real life would be where you're trying to, not everything mailed is this way, but when you're trying to mail something, it's based off of weight, and there's a span of weights that all cost the same amount. But as soon as you get just that 1 more ounce, that puts you above. You go to the next bracket. That puts you in the next one. Okay? And so let's go ahead and continue this as much as the graph will let us. This also works for negative. This is called the greatest integer function. It is going to be on your parent function, and it should be the easiest one to pick out because it's totally different than the others. So let me ask you, is this continuous? No, not continuous. What about the domain? If you're thinking, well, I don't know, just think, are there any numbers that you can't plug in for x? No, you can plug in any numbers, and even though there's a lot of breaks in the graph, you would just say, well, it's all real numbers because every x is included. Okay, let's talk about range. So the actual numbers in my range look like -3, -2, -1, 0, 1, 2. Those are the integers. Now there is a fancy symbol for the integers. It kind of looks like a fancy Z. We're just going to write integers though. Okay, so there's another thing that we can do with evaluating, and this is where our definition here is going to really help us. So what is the greatest integer that is not greater than 2.3? You can't pick 3 because that's greater than it, so we have to round down to 2. Okay, what about 5.89? Yep, round down to 5. Okay, what about -5.1? Now, if you're picking -5, that's actually greater, okay? So we have to always round down, -6. And then 4 is just 4. Okay? All right, so that kind of wraps up 2.2. Let's move on to 2.3. Okay, so this is talking about increasing and decreasing an average value of a function. We've already talked about some ideas in this, and after party I've kind of been feeding it to you, exactly what you're supposed to be finding. So you have general ideas, but we're going to kind of make it come all together in this lesson. So the graph of f of x is given. This is the graph of f of x. It's a piecewise function. You can see something that looks like a parabola, a horizontal line, some other lines. And I want you to tell me where the intervals of f are increasing and decreasing. These are just the y values. When you think of f, just think the range or the y. Where is the y increasing? And so this is kind of like positive slope, although lines have slopes. Other things, we don't really use the word slope to describe that, but we're going to kind of broaden that idea. But we're thinking of increasing like a positive slope. So let's go ahead and write increasing. Now in this case there are no coordinates, there are just letters, okay? So it looks like this first part is increasing, so I would do -infinity to a. Okay, and if these were coordinates, we would use the x value. And so what do you think? Do you think it's still increasing at a, or just right up to a? Okay, at a, it's changing. So we actually would put a parenthesis there. Okay, from a to b, in between there, it's decreasing. So, but then from b to c, it's increasing again. So we're going to union that. Again, I'm going to put parentheses here because at those points is where it's changing. We wouldn't say it's increasing or decreasing. What about from C to D? We're going to assume this is a horizontal line. That's not increasing or decreasing either. Okay, and from D on, that's a decreasing. All right, so hopefully you're getting the idea. It's not an overly complicated idea, but you need to be able to write this notation down. This is a really big concept in calculus. Okay, so we already said from A to B, it was decreasing. So we go ahead and write that. From B to C, we already included that. You couldn't have any intervals in both that are both increasing or decreasing. That doesn't make sense. You can have some that are neither, like C to D, but you couldn't have both. And so this last little piece from D to infinity, that's also decreasing. Okay, now problem number 2 is basically asking us the same thing, but it's giving us a function and we need to type this into our calculator, okay? Because you probably don't know what this graph looks like. Maybe you do though. Alright, so let's go ahead and in our calculator, let's type in x to the 2/3 power, so we're going to do caret parenthesis 2/3. Move this over here. Alright, and let's start with just a zoom 6. This isn't something we're totally familiar with. We know it's going to be some kind of radical, but it also has a squared in it. So this gives us a pretty good idea of the function. We can see that the first part is decreasing, the second part is increasing. The break here, or where it's changing, is right at 0. At x equals 0, it's neither increasing or decreasing. That's where it's changing, okay? So we've got a decreasing from -infinity to 0. We've got an increasing from 0 to infinity. So let's write that down. One thing that if you have a more complicated graph than this and it's not like obviously at 0, you can find, in this case we're going to find the min. I'm just going to go through these steps even though we already know. Remember that you have to go to the left of that min and press enter, and then it's going to tell you to go to the right. This is how you would find out what that x is if it wasn't obvious. And there may be multiple ones. Okay, so remember also this e is scientific notation for times 10 to the -6, so that's basically 0. So is the y. All right, definitely rounded to 3 decimal places. Those two numbers are 0. Okay, so let's write this down. Increasing was the second part of the graph, so that was from 0 to infinity. Decreasing is from negative infinity to 0. If it's not obviously 0, you're going to have to use your calculator to find the maxes and the mins. All right, next part, slope, rate of change. You've seen this since Algebra 1. This is the Greek letter delta. It means change, the change in y over the change in x. Off to the side of this, I want you to write y2 minus y1. This is a formula you should be familiar with, over x2 minus x1. That's the slope formula. This is the average rate of change formula as well. And keep in mind, this is average. Now, lines have a very consistent rate of change. And we had this on our last after party, and not everybody got it, so I'm going to make sure to address this in class. But I want to say this now. Curves, polynomials, or anything that are curved, their rate of change is changing, all right? And so it's not a constant rate of change like as in a line. So we think in terms of average rate of change, and later on we're going to use the phrase instantaneous rate of change, which you maybe have already talked about in physics. So this average rate of change, though, this is the slope of the secant line between 2 points. So I'm going to write a formula, but I'm also going to draw a picture to make sure you understand. Instead of y2, I'm going to do f of x2, which is essentially what y2 is, minus f of x1. I want you to get used to this function notation in these terms as well. And just see that it's the same math you've been doing, it's just using the function language. Okay, so let's say we had a curve, and it looked like this. And let's say we just picked 2 points. Here is the value of x. I'm not even drawing my Cartesian coordinate or anything, but I'm just going to label where x1 and x2. It could be any 2 points. Now, if I go ahead and draw the secant line, secant just means that it crosses through multiple times. Okay, in this case twice, whereas tangent would be where the line just comes and hits at 1 point. Okay, and that would have to be, something like this. But for here, there would be no tangent line between these 2 points. Obviously, if it's a line, a straight line, it has to cross through. Okay, this blue, let me label this in blue. This blue curve is obviously f of x. So what we've got here is we've got y values, okay? Our y value right here is f of x1. Our y value up here is f of x2, okay? And this line that I drew in red is the secant line. So if you wanted to know the average rate of change between these two x values, you would basically be finding the slope of the secant line. Okay, so you would do f of x2 minus f of x1, numerator, over x2 minus x1, denominator. Okay, so now what I want to ask you is, this rate of change in the blue curve is changing constantly. This red secant line is staying the same the whole way through. Do you think this is an exact representation of the rate of change? It's not. Okay, this is why we call it average rate of change. Okay, at some point this graph is changing not at all, like right here. Other times it has a positive increase. Here it has negative. It's decreasing. This secant line represents, though, the average rate of change. Okay. So for number 3, it says for this function. So here they're actually giving us an equation, a function. Find the average rate of change on the interval. Now they're giving us our x1 and our x2. This is not a point. Notice the brackets here. They're giving us 2 x values. So we are going to use this formula. We are going to be finding f of 4, and we're going to subtract f of 1, and put that over 4 minus 1. I'm not even going to do the graph. We can do this completely without the graph. So 4 minus 3, that's 1, and 1 squared is 1, minus, and then f of 1, 1 minus 3 would be negative 2, and you square that, you get 4. So it kind of bumped back the same numbers. We have a 3 on the denominator. So 1 minus 4 is negative 3, over 3 gives you negative 1. So in this particular problem, the average rate of change is negative 1. Now, let's go ahead and graph this, and let's just practice graphing by hand. So if you draw your x and y axis, this would be a parabola shifted to the right 3 units. So 1, 2, 3. Alright, and we're going to go ahead and practice our up over 1, up 1, and then our over 2, up 4. And we could continue to go, but this is going to be good enough for this problem. Okay, and that should go all the way down and touch. So this is my f of x. I'm only doing this not because it's a necessary part to do the problem, but to show you what the meaning is. Okay, now let's find where x equals 1 and x equals 4. And let's draw the secant line. And just for fun, let's find the slope of the secant line. It would be down 1, 2, 3, negative 3, over positive 3. That's exactly what we got right here. The slope of the secant line, which is what we set up here, is the average rate of change in this interval. Now, if we change that interval, okay, it is going to change the slope. This is why we have to have been given an interval. Now later on, we're going to tighten this up, and we're going to make this interval smaller and smaller and smaller until we have basically not an interval but a point, and that's going to be the tangent line, and that's instantaneous rate. That's where we're going with this. Okay, if you're thinking about like acceleration, that this has to do with acceleration and things like that, you're right, it does. Okay, so number 4. It says the falling object's distance from the ground is given by d of t equals 16t squared. And this is, the reason this is not negative is because we're just doing distance. We're not doing its height off the ground. This is kind of like the formula we used at the very end of last semester. It says find the average speed between 1 and 5 seconds. Now, speed is the rate of change of distance. So this could have just said average rate of change of distance, but it said average speed. So what we're going to do is we're going to do d of 5, d of 5 minus d of 1 over 5 minus 1, and you definitely have a calculator here because this is a word problem. So d of 5, if you plug 5 in, 5 squared, 25 times 16, that's going to give you 400. And if you plug 1 in, it'll just give you 16. 5 minus 1 is 4, so this becomes 384 over 4, which is 96. Now we do want to use units, and that's going to be feet per second. And so the average speed, the speed is changing. Gravity is causing some acceleration here, but the speed is changing. But between 1 and 5 seconds, the average speed is 96 feet per second. So part B says, we'll find the average speed on this interval. Now this should look familiar to you, even in your after party recently. So we're going to do D of d of a plus h minus d of a all over a plus h minus a. Now I want you to notice something here. The a's end up canceling each other out, and we're left with h. Now this should look familiar, like f of a plus h minus f of a over h. This is where we came up with that. It wasn't just something made up. It has everything to do with this, and this is why we practice it so much. Okay? So let's go ahead and plug it in. 16 times a plus h squared minus 16a squared over h. Alright, let's bring this down to the next line. I need to FOIL a plus h and multiply by 16, so I'm going to have 16a squared. I'm going to have an ah and another ah. It's going to make 2ah times 16 is going to be 32ah. Now you take as many steps as you need to get to this point. And then h squared times 16 is going to be 16h squared. minus 16a squared all over h. And notice that the 16s cancel, and I can factor out an h. So we do 32a plus 16h all over h. The h's cancel, just like how we could have predicted that would happen. And so my final answer is 32a plus 16h. And this is going to be feet per second. Remember, because this is a speed, an average speed. Okay, as h gets smaller, these 2 points are going to get closer and closer together, and we're going to go from finding average speed to instantaneous speed. And so think about what would happen as h gets smaller, or as h approaches 0. We would be left with just 32a. Okay, and 32 is very significant. That's the acceleration due to gravity in feet per second squared. Okay, bring your questions to class.